Good evening, good morning in California to everyone. I'm Shachar Kvatinsky. We are starting another session of the ACRC webinars. And today I'm very happy to have Professor Jan Rabaey. Jan is a professor at UC Berkeley, and he's also a CTO in the FTCO division of IMEC. Jan, thank you for coming.
Thank you. Let me just share my screen. All right, do you see my slides?
Yes.
Good. All right, good evening. It's a true pity that I cannot meet you in person, and I truly hope that's going to happen sometime in the future. But anyhow, so that we have to do what the situation gives us. What I want to do today is talk about something I've been playing around with for probably the last 10 years or something like that, or even a bit more, and has various aspects. But what I'm going to focus on one thing today is basically talk about human-centric computing, basically human as a computer, or basically augmented with computing. So again, we know that the world around us is changing. It's changing very rapidly. We are putting technology in the world at a ferocious rate. And the world around us is really getting very smart. And I just show some examples here of how traffic could become in the future, how robots can become assisted, how swarms of robots can interact to perform certain tasks, drones, something like that. So a world that's really getting augmented with all kinds of capabilities and providing a wide bandwidth between the physical world and the cyber world. Now, the question that immediately pops up in my mind when I look at this is, how do we humans live and operate in a world like that? How do we cope with all of these rapid changes? What can we do about it? And when you start thinking about it, there's only one single answer. And the answer is, we have to evolve with it. We have to basically use the same technologies to make us as human in the world around us more effective, more basically efficient. Now, the way to do that is to add technology to our biological being. I call it actually the human internet. It's a set of sensing capabilities that augment what we already have. The networking to allow these various distributed sensors to talk to each other, to basically have computation to interpret the data and ultimately go back to action. And this platform should be obviously open. If from the time you're basically stuck with a number of limited players, you end up with limitation and you limit innovation. So what we're really looking for is to create this open, scalable platform that enhances human capabilities. And we'll talk about some of those capabilities in a second. So what we're going to focus on today, there's many aspects in this, but what we're going to focus specifically at today is the computational needs of such an environment. So again, why is this useful? Well, if you know our human body, our brain actually performs two major functions. On one side, what it does is make sure that we survive. It basically monitors our biological systems, adjusts them, make sure we get energy to the right places, and so on and so forth. So this internal cycle. And then we have the other part, which basically is how we interact with the world, to our very 7 senses that we have, as well as the motor function that allows us to impact the world around us. So in some sense, we're trying to supplement this by adding, again, a whole bunch of environments around the body, basically what I would call create a physical human avatar. And since that data ultimately is now all digital, all connected, we potentially can also put this as a digital human avatar, a presence in the cloud that basically mimics our basic operation. Now, I'm not going to talk about the second part. I'm going to focus primarily on the physical human avatar because, you know, digital human avatars is something that's still a topic of discussion. Is this something you really want? Now, human avatars to me are very relevant in this pandemic times, right? We already know that, for instance, if you want to observe COVID, there's a whole bunch of factors that can show onset of COVID. It could be blood oxygenation, it could be breathing rate, it could be heart rate, it could be temperature, it could be a variety of things, breathing, and so on and so forth. So having something that helps us to monitor this type of functions continuously and live without having to go offline is important. Now, in order to make this happen, we need to come up with a number, we have to address a number of constraints. Systems like human systems typically operate at millisecond type of latency rate. So most of the functionality only works when we have latencies below that millisecond type of response times. It obviously should be extremely robust and reliable. Obviously, it impacts our human life. So we want to make sure that the system is operational. It has to be secure and private. Again, this is, we are now going to our inner core, and it has to be transparent. So here's some of the functions that people have been playing around, and sensors exist for each of those. Basically, there's a number of biometric parameters we can observe: temperature, heart rate, respiration rate, blood pressure, blood oxygenation, blood glucose, bioelectronic signals, EMG, EEG, ECG, and so on and so forth, and motion. And those can be monitored in various places, and some of them are better basically at the wrist, some are better at the wrist, at the chest, at the leg, or even internally. Like if you look at bodily fluids, some below the skin or implanted devices might play a role as well. And there's some other derived parameters like sweat, stress, fatigue, emotion that can be basically created by a combination of those parameters. And as I already said, people have been very innovative in creating flexible sensors for a number of those modalities, but typically they're basically in a standalone mode. They're a single device talking to a cell phone type of setup. And what we're trying to do in the human internet is actually combine those things together as a network that can be flexible, dynamic, and changeable. Now, as I already said, we also want to go beyond pure monitoring or reaction to basically internal behavior. The other option that we need to have, or we were looking for, is can I actually improve the way we as humans interact with the world does? Can we get better vision? Can we get better AR, better nose, better taste? Can we get senses that we don't have right now? Can we look in the infrared? Can we hear ultrasound? Things like that. And one example, I think, for instance, that I've been looking at and I thought is really interesting is this whole space of hearing, or hearing aids, or hearables, as we call them these days. Hearing is a fairly complicated function, but actually for after a certain age, you can see some degradation. Now, by adding basically microphones, and amplifiers and electronics, we actually can think about smart hearing. But you can do a lot better than that. If you start actually putting more microphones in different places of the body, we can do beamforming. We can basically use eye tracking to figure out where the attention is, beamform in that direction, and so on and so forth. Many different opportunities to make hearing a lot smarter. And again, it's not just in the ear, it actually could combine various pieces of information. And one piece of information that helps quite a bit is information about what the brain wants to do. If I have some information about the stress factors, the mind, the intent of the person, I can actually help that to steer my sound tracking in a particular direction, cancel some of the noise, and so on and so forth. So people are looking, for instance, at using, since the hearing aid is in the ear anyhow, why not add, for instance, EEG to it so that I can actually measure some brain signals to help basically improve my hearing. And there's quite a number of projects in that particular base. Also, projects coupling brain-machine interfaces to hearing aids. Brings us actually to the, it's kind of the, to me, the ultimate augmentation that we can have as a human is when we basically connect directly to the computer that's at the core of a human being. It's our brain. And if we basically, brain-machine interfaces help us to observe what's happening in the brain at various places, extract that information, analyze it, classify it, and potentially lead back to actuation. Over the last so many years, my group actually, together with other faculty here in Berkeley, have been working on a variety of those brain-machine interfaces. Some of them very implanted, very invasive, some of them not so much so. But the idea is indeed helping, basically getting intent from the brain and use that information to perform certain tasks. Now, fairly complicated, obviously, type systems, they're implanted, they have to be obviously very robust, reliable, all the type of things we're talking about. But something that was like a dream 10 years ago actually is starting to look more and more like reality. For instance, some of the work we did, some of the chips we did ultimately made it to Elon Musk's Neuralink company, which actually is trying to implant thousands of electrodes in the brain and actually connect them outside with a high bandwidth connection to perform certain actions. And right now he actually has kind of monkeys playing video games with it. Fairly first step, but amazing that in this short period of time, 10 years, we see this technology actually evolving quite rapidly. Now, again, I want to state that a pure brain-machine interface that only looks at the brain itself might not be sufficient. To get the real effect, you need to combine various pieces of information. If I can also measure tension, stress, emotion by skin conductance, motion by 3D accelerometers that basically measure my activity, how much I basically I'm moving around, all those things combined together lead to a much bigger picture of what intent is and how to do a job in the best possible way. So this just gives you an example of all the opportunities of what a human internet can give you. So now the question is, what does it take, right? How long, what are the type of things we need to do to make this all happen, to make this kind of dream of a human internet reality? And again, there's a whole bunch of factors that I already mentioned some. First of all, obviously, it has to be wearable. If some things are obtrusive, devices that are obtrusive are not going to be used. So wearable, flexible, conform to the body, small, miniature, all those things are very important. The second one that I pointed out is that it's not about individual devices. It's about a network of devices. So it has to be, you have to have connectivity, functions are going to be distributed at various places and so on and so forth. So the networking aspect is very important. Energy is crucial, right? This device has to be miniature, already said. So we are really pushing at the boundaries of what I can do with a nanojoule or a little amount of energy. Sometimes it's harvested, sometimes you use batteries, a combination of the various factors. So efficiency is crucial. It has obviously to be safe, robust, and secure. We mentioned that already. But the last one, and that's what I'm going to focus my talk on today, it has to be smart. It has to be learning how the body behaves, the specific signals of a particular person, and basically build type of reactions as a result of that. So what I want to talk about today is that learning and that smart part of the human internet. Now, if you think about the type of computing here that we are considering, the type of computing that we need to have is very different than the way we typically think about computing. It is about interpreting signals that are noisy, that are highly variant, that can have interference and so on and so forth. Look at those signals, extracting certain features, and using those features ultimately to classify, to basically determine and decide on actions and performing those actions. That's really what we're talking about here from a computing perspective. And as a result, it basically resembles a lot more to what basically the brain does than basically what traditional computers do. If I look at a computer as it is today, as we've been building it since the last 50, 60 years, our computers are built to execute algorithms. So we have a sequence of actions we want to perform, instructions we perform, and we execute them. And the goal of the design of those computers is really to maximize performance while minimizing energy and cost. That's the way we have been thinking about computer architecture forever. Now, if I look at the brain, which is kind of the equivalent of what the system we're trying to build, the goals of the brain are very different. It is not about executing algorithms, it's about survival. It's about prospering, it's about procreation. That's what our brain basically has been evolved into over all those ages of evolution. And as I already mentioned, it does this by basically combining two loops. On one side, you have the inner loop, which basically observes how our system behaves. It measures a whole bunch of parameters, heart rate, temperature, all those type of things, lack of energy. It observes those and basically translates them into patterns. Actually, it observes patterns of firing, for instance, of various neurons. Based on this, it basically translates it. If you go to the brain now, the small patterns you originally observed from the various sensors are being combined and fused together in larger patterns. Those large patterns are then compared to what we know, the stored patterns, what we typically would like to see as behavior. And based on that, we have motor function, we predict output patterns, and we adjust the system. So it's a loop basically that basically helps us to basically survive and to prosper. But then the other side, we basically, in order to prosper, you also have to read the environment around you. So you have the second loop, which is your behavior loop. The outer loop, which basically does very similar things, but basically uses our various interface to the world, the various sensings we have, and the motor functions that we can execute. So the mission is very different. And the goal, basically the metric we're using, is basically maximize reward. Humans basically try to maximize the outcome at a minimum energy cost. So it's kind of a different mindset of how computing can be done. But the more important thing that I want to point out here, it is basically computes with patterns. Patterns are the way we basically represent information and store information in our brain. So this kind of leads us to maybe rethink a little bit how we should build computing elements for the human internet. I believe this concept of computing with patterns is very important. It's basically, you look at it's a network of neurons. Basically, when you see certain firing patterns, you know that certain actions are being taken. Now, the important thing also is that those patterns are approximate. They don't basically always resemble each other. They basically are similar in a certain sense. And very often they're analog or discrete. Learning is continuous and incremental. We don't basically download a piece of information in one shot. Basically, now we continuously adjust how we perceive the world and how we react to it. I also think it's very important that every single brain is different. It's customized. For every single person, basically adjust the whole system based on their observation of their position in the world and so on and so forth. And obviously it performs sensor fusion, basically uses multiple sensors to create information and reactive behavior. So this is interesting and actually helps us to think about maybe how should we build that next generation. Now, one thing I really want to point out that has to do with this continuously learning aspect, I think plasticity is essential. If you look at machine learning these days, we see a lot of this big data. You collect huge amount of data, you build a model, and then you distribute the model and it's fixed. That's not sufficient. In a world that we live in, actually continuous learning and adaptation to the situation at hand is absolutely essential. We have to be able to deal with changes, with novelty situations we haven't seen before, things like that. And again, customized to the environment and the user. So plasticity to me is another important element. It's a system that has to be continuously evolved. Now, to make this all happen, we're not there yet, obviously. This is a dream. And I believe that in order to make such a system really work and being deployed in a broad sense, we're looking at improvements in many different ways. Basically, latency, robustness, performance, you name it. Basically, I say we need 100x in every single metric you can think about. So learning-based systems, obviously, they're big right now. If you look at the evolution in computer architecture, almost entirely driven today by machine learning. And it's probably worthwhile to look a little bit at the landscape as it has evolved, right? So machine learning is a approach where basically a computer doesn't get programmed by a set of instructions, but basically by observing data. And you have a whole bunch of them, support vector machines, belief propagation, graphical models, you name it, right? So that's the big picture of machine learning. Now, within those, and the most successful part of this today is the one that we call neuro-inspired. neural nets, basically. And you can think about digital neural nets, convolutional neural nets, deep nets, reservoir computing. And one particular one that I'm going to talk more about today is high-dimensional computing. And then the last class is the one which is what we call neuromorphic, is where you indeed try to build something brain-like. Neuroinspired basically just uses some concepts that are basically observed from the brain and tries to translate them into computational engines. Neuromorphic really tries to build computers like brains. And spiky neural nets and Boltzmann machines, computing, oscillating networks, they're all kind of similar type of ideas, but basically try to say, kind of build the neuromorphic type perspective. So all of those are very effective, but the real challenge is, again, that factor 100x, the factor 100x, but also the fact that we need plasticity. So if I look what has happened and what's on the market today, or what has been published or basically presented at various conferences, you see that there's a broad range of implementation of machine learning type of engines. Using the different platforms, some of them GPUs, ASICs, TPUs, FPGAs, you name it. Now, if you look at this plot here, which comes from Tsinghua University, which basically has combined all the various approaches in a single set of spreadsheets. On one axis, we have power. The other one is the computational requirements, the number of operations per second that are required. And you can start seeing that, if we look at GPUs, we get about 10 watts of power or something like that, very programmable engines, but about 0.1 teraops per second or something like that. If you want to get to higher performance and more energy efficiency, you have to basically push more and more towards ASICs or very specific functions like, for instance, in-memory compute. So that's really where we want to be. If we want to basically talk about human internet, I want to be somewhere that's 1 to 10 petaops per watt approximately. Again, that requires us to basically improve performance and energy efficiency dramatically. Because really, this is what the area we would like to be. Now, people have actually made progress on this chart. You can start seeing some of the yellow dots, some of the red dots, some of the green stars actually are getting very close to those numbers that we basically are basically desire. The question is, how did they do this? Well, the first one was, as already mentioned, right? You do ASICs. You start building engines that are very dedicated to a particular paradigm, and you basically create a data flow machine almost. And a lot of those basically are now, you have these accelerators that are basically multiply accumulative array with very specific memory interfaces and so on and so forth. And people have shown up to 10 TOPS per watt by, but only inference, by the way, no learning, just basically executing a model. So that's an example of what they can do by dedicating the hardware to the core of the computational engine. Now, to get to that 10 teraops per watt, actually the designers of this particular chip here, there's the group of Marianne Verhelst over in Leuven in Belgium, they did something more. They used all the tricks we have been using in design forever for the last 10, 15 years, dynamic voltage scaling, dynamic frequency scaling, depending upon what the results are, you can actually adjust and crank the buttons in such a way that you get better energy efficiency if you basically need less performance. But this group also observed that you don't always need the same accuracy. For instance, in early phases of observation of something, you can get away with a low accurate type of computation. And then when you start zooming in, you crank up basically the accuracy. So actually it brings a new paradigm. Instead of basically only voltage frequency scaling, we also can scale dynamically the accuracy of the computation. Or we start going slowly but surely to computation which varies number of varying resolution and correctness. So that's one trick that we can use to improve. Second one is to observe that if indeed I don't need the accuracy and I can be approximate, we can go one step further. Rather than implementing this whole multiply accumulate array in the digital space, why not implement it in analog? Analog transistors are very good at performing multiplication. Not very accurate multiplication, not a large enough signal to noise ratio, but they're very good at doing multiplication. So I can build my neuron array, my multiply accumulate basically array by basically having a analog computer basically built. And again, here one example, this work done by the group in Stanford, which basically built a switch capacitor processor for data accumulation. Now, the interesting part is that we know one step from variable accuracy to really statistical accuracy. In an analog computer, you don't know exactly what the result is going to be. You get a distribution. And the task of the designer is to make sure that the distribution is narrow enough. So based on variations in the transistors, variations in the technology, we basically find some design tricks to control the accuracy, for instance, by calibration, by basically adding enough random elements together, the laws of numbers and things like that. So that's the next step, is statistical computing. Approximate computing is a way for us to have better energy efficiency. But then you start realizing that if you just focus on the multiply accumulate array only, you start seeing that some particular problems that emerge there as well, that ultimately now the power is not going to be the accumulate anymore, but actually is coming from fetching the data, the weights and things like that from your memory and bringing it to your multiply array. So the next step that people have taken is, okay, why not merge the two, basically do in-memory compute. Where we basically have analog computation happening in an array of resistive or smart memory elements. Again, there's a lot of publications in this space. A lot of it is not very scalable, but there's actually some very promising efforts going on that show actually pretty amazing numbers in terms of energy efficiency with some state-of-the-art technologies. And I just want to quote some of the work that's going on at IMEC in this particular space, using some of the non-volatile memory technologies. So very exciting, but all those things, all those trends that have happened basically don't address the problem I was raising up front, plasticity. We don't do inference only. If I think about my human internet, I want to have something that evolves with the situation, that basically can learn on the fly and adjust. So plasticity is important. That's why I've been kind of looking at, I got by accident attracted to this domain by meeting a person called Pentti Konerva. Pentti is a computational neuroscientist, originally from Finland, but basically now at the Redwood Institute in Berkeley, who's basically thinking about how the brain operates and see if this basically can translate into some computational paradigms. And then particularly has been looking at the cerebral cortex. So the cerebral cortex is a big part of the brain, actually. The cerebellum is a very huge component, and cerebral cortex, basically, if you look at it, is the diagram here, how the neurons are connected here. If you're the designer, you kind of recognize what this structure is. You can start seeing, if you can see my mouse here, you have the input lines go to some neurons, which basically perform a decoding function. It's like a decoder in a memory, but it's not a typical decoder, it's a random decoder. Basically, it combines signals together in a random fashion. This then connect to your, what we call the parallel fibers in the brain and the cerebral. The parallel fibers, basically, that look to me like word lines. Then you have a number of neurons we call the Perkinia cells that look like memory cells. That's where storage is done, and ultimately you have word lines that go to the output buffers. This is a memory, structured like that. But it's a memory that's not your traditional, it's more what we call an associative memory, where you apply a pattern, you match it to what I stored in my information, and when you have information that matches, you get some signalization at the output. So it's a large associative memory. So this made us think about, and Pentti think about with some other folks in the same community, about a computational approach that is statistical. Again, these things are all based on random information. There are no deterministic patterns here. It operates on patterns. Things basically are, as I said, it's associative, it's based on pattern matching. It is approximate, it's not correct match. It is from the time we were somewhere in the neighborhood, you're fine. Interesting that it performs, I'll talk more about that in a minute, it computes in superposition, right? Information is overloaded on top of each other in those patterns. It supports reasoning. It continuous learning. You can basically adjust the state continuously. And as I said, it's centered around associative memory. So this is very exciting, and we've been playing around with this. It's like, is this an opportunity to build this, indeed, these very inefficient, efficient computers that can help operate my human internet? So let me explain a little bit what the concepts are behind it. This is okay. As I said, basically, we're going to present data as patterns, not as numbers, but as patterns. And actually, patterns are, to me, random vectors of high dimensional nature. Dimensions could be about 1,000 or more, where the elements could be a variety of things. They could be binary numbers, zeros and ones. They could be binomial, basically -1, 1. They could be integers. But most of the time, we operate with zeros and ones. Now, there's an interesting feature. If you take two random vectors of high dimension and you compute their Hamming distance, you take a random vector of 1,000 bits, another random vector of 1,000 bits, you XOR them and you measure the pop distance, the pop count, you observe that the probability that those vectors are going to be nearly orthogonal is going to be extremely high. And the higher the dimension, the more orthogonal they will become. So the probability that 50% of the bits are going to be different is about almost for certain. So by picking random vectors, I basically create an orthogonal base with which we can then basically perform computation. So whole ID, random patterns, we use those to form an approximate basis set that then can be processed to encode relations. What we're looking at is not encoding a mathematical function, but we encode relations between various patterns. And once you see two vectors that, when they're queried, show that they're actually that they're close to each other, they're not orthogonal, that means typically there's some relationship between them. So that's the basic idea behind the whole thing. And then we can perform operations on them. Like we have those patterns that I showed you, they on brain, you basically combine them together. And there's a number of things I can do. Like I take two vectors and multiply them together. They bind two vectors, get a new vector, which is orthogonal to the original one. And is dissimilar to its constituent vector. So I can do multiplication, very simple XOR basically. You can do permutation. Permutation is kind of swap the bits around. And as a result of that, I get something which is, again, orthogonal to the original vector, but there's something that's very effective because it's invertible. I can use it to represent sequences. Sequences are very important in the signals that I'm dealing with. So multiplication and permutation are invertible and preserve the distance when we do so. The third operation we do is addition. Addition is basically max count, or basically, and it's actually similar to superposition. But when I add two vectors together that are somewhat orthogonal, the resulting vector will be analog to the, basically be similar to the two vectors it's created from, right? So you combine vectors together, you preserve this similarity. It's really good to help us to represent sets, to bundle things together. It's not invertible though. When you basically want to decompose it again, you might have some errors sneaking in that you have to remove. So this is my whole algebra, patterns, and I combine those patterns together. The last factor computation I have to do, which is very important, which is done typically in my associative memory, is compute the distance between two vectors. Look at similarity. What is the closest match I can have? I have learned in the past and that I basically can relate to. So this is measurement, typically could be Hamming distance or could be cosine similarity, depending upon the representation you use. So let's see how you can use this to do some computation. Here's an example of a system we built. Combines actually very many aspects of the human internet. It's based, it's actually a gesture recognition system based on EMG. So we have a electrode, which is flexible printed electronics. Actually, this was just published in Nature Electronics about a month and a half ago, 2 months ago. So you have the flexible electronic electrodes, basically on the arm, measuring your EMG signals of your various muscles with a spatial type of pattern. It doesn't really, it's overdimensioned. It doesn't really care too much about the exact positioning, since in this case I have about 128 or 64 sensors, so more than enough information. This information is then transformed into using a particular chip we designed for brain-machine interface, but works perfectly for this as well, is then basically the data is acquired and turned into digital. So we get a set of input streams of basically some EMG information. This we then feed into our high dimensional engine, which is a small little processor in this particular case, to basically do the classification and ultimately show gestures and use those gestures to perform action. As you can see here on the right is one of our graduate students wearing the electrode array and basically doing particular handset gestures to control basically a robot arm to basically move particular actions. And once you have classified the gesture, you can do basically anything with it that you want to. So again, it's based on, we have a set of spatial temporal sensor streams that are coming in from the electrode array. The important thing is that this system learns very quickly. It's one-shot learning. It actually, once you do a gesture, it learns that gesture and can start basically recognizing it. Obviously, the more you train it, you can basically improve on it by basically adjusting the stored information gradually. It is very lightweight. It is customized to a particular user and the wearer. So if you basically put it on another person, it won't work. You have to retrain it again. And it also is robust against change and variation. So how does it do this? Well, here's kind of how the HD processor works. We have our various EMG streams. These are the blue waveforms that you show here. These are very simple electronic waveforms. You can sample those at a particular time slot, let's say R1. I get a number of measurements from my various sensors. Okay, so I have one vector, which we then going to translate into a high dimensional vector in a second. And then you keep on sampling at various time slots. So that's, you have your spatial information coming from your different channels and the temporal information from the consecutive samples. So the engine we basically do is very simple. You take your input streams and we do some processing on it. There's some nudge filtering and some removal of noise. But ultimately, the next thing we do is take each of those channels and map it into our high dimensional space. We basically know that channel 1 is represented by a single random vector that we have learned or basically stored in a memory which we call the item memory. So we have one random vector representing each channels, and they're all orthogonal. And the data we're getting also, we're mapping into this continuous data. We also map those into high dimensional vectors, let's say dimension 10,000 to 10,000. And then we do combinations, right? We take the channel, it's like a key value pair. I take the key, which is the channel number, and I multiply it or I bind it together with the information of that particular channel at time slot 0. So you do that for all your channels, and then you add them together, you bundle them together as a set, and now I have a single high dimensional vector representing time slot 0. Now, obviously, we also need temporal information. The way you do that is basically by combining, it's kind of like, almost like a filter as you would look at it. It's permute, multiply, permute, multiply. I create basically n-grams. It could be trigrams, pentagrams, whatever. That captures your time information. You get now and you slide the window over your whole time domain. For every time slot, I'm getting in one particular vector. We add all those together, and in the end, I get one high dimensional vector, which is representing that particular gesture. And I store it in my associative memory. Now, in order to do classification, you do the opposite. You take a waveforms coming in, you encode them, and you look in the associative memory for something that's a close match. Once you get a close match, you say, okay, that's the gesture we get. So all of this is based, as I said, on computational with random vectors. There's no number computation here at all. It is straightforward. Now, this works actually amazingly good. For a number of the cases we tried this out, you basically get 95% accuracy. But there's some challenges that in order to make this work in real situations, you have to basically realize there's a couple of things. Number one is you have a set of gestures, like in this case, there's about 23 gestures we're playing around with. But there's another fact that plays is how I position my arm. If I basically change the way I hold my arm, my EMG signals will change as well. They are depending upon the environment or the context that they're basically generated. And if you would basically just learn, let's say, in one position, I have my arm held like straight in front of me. If I hold it only in that position and I only train for that, you will see that once I then move my arm, I might not get very good accuracy anymore. So you get a degradation of the results. And this might be true because of arm movement. It can be also the fact that I get, if I wear the device for a long period of time, the sensor may slip. Or one day after the other, I can take my device, I take it off in the evening, I put it back on the day after, the sensors are not in the same position anymore. So you have to deal with changes and flexibility. And this shows how well it works. Like here, for instance, here's the green is over a couple of users here, where we train in one position, and you get accuracies like it shows here, about 94. This is all measurements actually, as I said, most of the time we're basically in the 90s. Now, if I use that, what I train in position 1, and I use that to do classification in another position, you see a dramatic drop in accuracy. But now what I can do is be smart. I can start merging the experience. I can start manipulating of what I remember. I play around what I store in my associative memory in such a way that I maximize my accuracy. And that's interesting because now we start playing around this with what is the information that I should remember and how should I represent my information? Should I keep separate prototypes for each position, or should I find a way of combining them? And the interesting thing is actually you can kind of look at it and reason about this. Like here is an example. We have 13 gestures that are basically applied, and you can see various trials in various positions. This, by the way, is mapping what we store in associative memory. As I said, it's a high dimensional vector, 10,000 to 10,000 bits. We use actually UMAP to map this into a two-dimensional space so we can plot it. So be careful, this is just a representation of a very high dimensional space that's very hard for us to basically see. But what you see is that various trials of a particular gesture in a certain position tend to cluster together. But still, though, you can see that for the same gesture, like the purple one here, they can occur in many different places depending upon the position. And the second space shows the same set of data, but now basically coded for the various arm positions. And again, you might see that there's very different ways of representing this. So the question is now how to optimize this in such a way that I get the maximum accuracy, but also maybe how to reduce the amount of things that I have to remember. If I could actually find a prototype for each of those clusters here and store them all in memory, but that's a lot of memory, maybe it's a better way for basically optimizers. And actually we found a number of ways for us to optimize what I store, what I remember based on various conditions and plasticity. And again, here's an example where I just use one single prototype for every gesture, but I've chosen in such a way that I maximize the overall response. It's actually 99% overall gestures and positions, versus basically having prototypes for every single motion or every single gesture, every single position. So that gives you some ideas of the type of things we're playing around with. There's a lot of interesting other things that are happening, but it's just a snapshot of what we're playing around with. Now, question is, again, going back to the beginning of my presentation, I said, we need factor 100x. Why do I believe this style of computation here that I was talking about has the potential indeed to give you the 100x improvement in energy efficiency, performance, simplicity, and so on and so forth? As you can see, the computation that we are doing is actually very straightforward, right? It's basically just long vectors, binary, and we do very simple local operations, multiply, add, which are basically don't have any, basically bit by bit operations. Very simple. The only complex operation we're really doing is the distance computation, where you have to basically go over the whole vector. Now, this we can capture in a processor architecture that is basically mapping that basic idea. So rather than operating on with an ALU or something like that, we work with very high data, very wide data words that can be 512 bits, 1000 bits, basically in parallel. As I mentioned, the operators are simple, so they only perform on local information, so there's no global wires. So it's only local interconnect. And the processor itself is very simple. You have an item memory that basically stores your random patterns. They can be stored, can also be generated. There's some very interesting ideas there. And then you feed it to a number of pipeline stages that does this computation that I showed you, multiplication, addition, permutation. Ultimately, you add all these things together and you get a single vector, you store it in your associative memory. And here's the processing element. The DPU is very straightforward. It's just a couple of gates. So a very simple processor to perform this. And you can see the energy per prediction is around the microjoule range for a variety of applications, face recognition, cardio, EMG, language recognition, classification, things like that. And when you implement this in a dedicated format, you can see that we outperform with basically with our, I call this our HG processor or HPU, is basically about a factor of 3 orders, 4 orders, or 5 orders more efficient for the computation than the CPU or GPU does. So this is, by the way, numbers that we got from a 28 nanometer CMOS realization. Now, looking forward, why is this kind of exciting? So it shows good results, and it's very useful for the type of single processing that we're basically interested in. But I think this goes further. If you think about scaling energy, the only thing that the ultimate knob we have in scaling energy is scaling supply voltage. Because we know if we still scale supply voltage, let's say to 100 millivolt or below, things start to happen. Things like basically errors are going to happen. We get variability, we get all this type of thing, noise coming in, errors are happening. Now, typically for a normal digital computer, that's catastrophic. But here, because the fact that our information is stored as random patterns, and we only care about proximity or similarity, it is basically a computational approach that provides graceful degradation. When we start seeing errors happening, the system still works fine. Actually, you can go, if you have a vector length of about 10,000 bits, you can see you can go 1,000 bits wrong and still no impact on the accuracy. It's only when you start getting around 3,000 bits, 30% of your bits basically being wrong, that you start seeing some degradation. And we can actually use our associative memory as a form of regeneration. When a signal goes wrong, you feed it back into your memory and you clean it up, just like a digital gate performs regeneration. So this, to me, is a great opportunity to think about computation in extremely scaled regimes. And that's kind of the ideas that we've been playing around with. And that kind of motivated me to basically look a lot more into this computational approach. So once you start thinking about this, and I say, okay, now can I indeed try to do something like that in a nanotechnology? And this is some work we did together with folks at IBM and Zurich, where they actually show that you actually can do very nice in-memory compute using PCRAM. It was a paper that was actually published in Nature Electronics also about a year ago, or no, even less than that. And then there's the other approach, basically using advanced technologies such as 3D stacking combined with RAM and carbon nanotubes to basically build a HD computation engine. This was worked together with a group of Philip Wong and Subhashis Mitra at Stanford. Max Schulacker was actually the key guy. He's now a faculty member at MIT, pushing some of those integration technologies to the extreme. But the beautiful thing was that indeed we could build an engine with in-memory compute on those advanced architecture, even when there are plenty of errors happening. I think the system was still operational. So I think this is exciting. I think helping us to basically set the setting of thinking about how humans operate and see is there an opportunity for us to rethink the way we do computing, especially in the context that I've been describing about. I think there's plenty of opportunities here, and that inspiration from nature can help us to push forward our next generation of computing devices. I already talked about cerebral cortex with the associative memory, but there's many other things. If we look at the hippocampus, where we basically do how we as humans or basically animals like bats and any other one, how they basically find their way in the world is that they actually have a grid of neurons. It's called the placenta and the grid cells that basically act as a spatial map. A very efficient way for us to basically do tracking, positioning, and so on and so forth. Pretty amazing how it worked. Maybe we can use this as inspiration to build our next generation tracking engines. Or just think about how our olfactory system works and how it's structured and how it combines low dimensional data with high dimensional data, and so on and so forth. So many opportunities for us to learn more. And that's why I think we should keep working with the people over in the field of computational neuroscience and things like that to figure out, hey, can we build more efficient engines in the future? And with that, I would like to acknowledge all the people. There's many people have been contributing to this, but primarily Ricky Muller, Pentico Nerva, Anna Reyes, and other ones as well. Thank you for your attention.
Jan, thank you very much. We have time for questions. You can ask questions in the chat or raise your hand. Tzachi? Tzachi, you are mute. I need to unmute you.
Yeah, ask to unmute.
Okay.
Okay.
First of all, thanks. Very interesting. I'm wondering about the following thing. You actually described something as a phenomenon which is a very sparse space.
Mm-hmm.
Multidimensional space is very, very sparse, which is why you get the orthogonality. Now, viewing it from a, let's say, coding perspective, like error correction codes,
Mm-hmm.
you may be you're doing kind of cheap coding,
Correct.
very inefficient in the coding sense, but apparently winning in the bottom line of the, cost performance or power performance or things like that. So what I'm wondering is whether this is something truly inherent, or the next step will be that some smart coding people will come and say, okay, so we understand that the game is different, but we can still come up with codes, so to speak, that are much better than the codes that happen, not by design, but by nature.
Correct.
Any thought about this?
No, absolutely. This obviously is from the time you talk to anybody who's an information theorist, they say, oh yeah, these are random codes, right? That's what you're going around it. And absolutely. Now, you hit the right thing there. The fact is that I don't really care about code construction too much at all. It's very straightforward. I actually these days we use actually some automata, automata based generate by codes randomly. That doesn't matter. We take a seed and bingo, let it go. And the operations themselves are very straightforward. So simplicity is really crucial. So so there's two options, right? I can go for better codes, or if I figure out that I'm basically pushing against capacity, right? There's always a capacity. How much information can I overload onto a single vector? If I figure out that my space gets too dense, I just increase this vector size. I increase my space. And indeed, as I said, typically we operate at extremely sparse spaces. We're trying to do that as much as possible because it preserves accuracy and performance of the overall system. But yes, there might be smart things you can do. We've been thinking a lot about sparsity. Can I basically structure my vectors that I use to be sparse, and this way basically reduce the number of operations I can do? Can I find other ways of but then the question is how much will it complicate my computations? Again, we're trying to avoid anything which is complex. Anything that's integer, anything like that basically costs me too much energy. But absolutely, I think this is a good question. And we do think a lot about capacity, by the way. There's a bunch of papers that basically describe how much information can I load. At what point in time do you start forgetting things? If I put too much stuff in there, I might start forgetting information, which is a natural thing. You say, okay, I'm overloading it. Maybe I should basically increase my memory size.
Okay, so you're basically saying, hardware-wise, you're spending memory, tons of memory, in exchange for simplicity of computation,
correct,
of operations, and robustness in the big picture, at the big picture level.
Correct. The robustness, for instance, the memory, it's not tons of memory. Actually, for most of the cases we're having, actually, the amount of things I have to store is relatively small. And definitely when you start generating a random vector, we don't have to store this either. So again, I can be approximate in my memory as well. I can afford the memory to make errors. And as a result of that, I basically, again, get some good gain in efficiency as well.
Okay, thank you.
Okay, other questions?
There's something in the chat room, I think. I know.
You know, in the chat is, it's not a question, it's a fact.
No question, good.
Yeah. So I see that Tzachi has another question.
Good.
Okay.
Go ahead.
Yes. Another question has to do with the communication aspect, not in the sense of a body internet, but rather within the memory itself. How close do the bits, when the bits that need to interact, even if it's a simple operation, are close, I can see things happening nicely, efficiently, etc. So that's okay if you do a circular shift or some kind of operation among physically adjacent vectors. But can you really always, does this limitation of proximity limit you, or does it happen that that's all you need?
It's all we need, actually. This is kind of almost by design, right? You don't basically try to put things, and the circular shift is the example, right? If I do permutation, there's many different ways of doing permutation. The circular shift is the easy one. I take a vector, I shift it to one position, you XOR the two together, you're going to be orthogonal.
Sure.
It's beautiful.
Yeah.
So the only complex computation we perform is indeed the distance computation. Because for a distance computation, I have to combine over all my bits of my vector together. And that requires a combination factor. So that's the most expensive operation you have. All the other ones are purely local.
And what if two vectors are not adjacent in the memory? You need to bring them from somewhere to.
Yeah, no, you're right. So obviously, memory itself is a way of scrambling information, right? Because memory is you apply a data word and you basically match various lines, something like that. So again, yes, that's obviously the most expensive operation we're dealing with. When you basically have to access your associative memory, depending upon the size of that memory, will determine how much energy efficient you have. Fortunately, for most of the cases, you think about it, how much, if I do my gesture recognition, I have 13 gestures, I might maybe have about 100 words in my memory. For this particular case, it's not a huge memory. Typically, the amount of classes or the number of classes you have is relatively limited. And so we don't have to deal with very large memories. But even then, you can do clever things, right? Like what Philip Wong did and Supershit. They basically combined the computation right into the memory cell. They have this, it's like a column, it's like a flash memory, where you stack layers on top of each other. You have a column of transistors, basically. And by the way you construct that column and the connections to it, you actually start performing you implement certain computations.
Philip and Subhashish, they use the memory for the computation or the carbon nanotubes?
There were two things, but there was actually, within the memory, there was computation itself. Some basic
okay, so it's analog computation, okay.
That is correct.
Okay. Okay, another question, Ofer, it's good to see you. You should be able to unmute yourself.
Hi, I wonder how do you set in advance the size of your memory, size of your vectors, number of sensors, number of channels? What is the magic behind that?
There is no magic. It's very often hard work. There's things we play around with. Obviously, you have to perform. Like the first thing you have to decide is the form of your encoder. Right? You have a set of channels. How do you encode the information? In a neural net, that's something that the network itself is going to learn. We don't. We basically try various ways of how to encode information. How many? Let's say what type of n-gram to use. How much temporal information do I want to store? How to combine, if I have, let's say, diffuse heterogeneous sensors. Like for instance, if you look again at this arm position, I can have an accelerometer measuring the arm position Well, then I have my EMG signal. Now, how do you combine those two together? Do you classify them first or combine? This is actually, again, this is design. It is not something, there's no magic there. It doesn't go automatically. We basically play around with some feature. And if there's a way to automatically generate those things, that would be super. But right now, it is handcrafted, for sure.
Okay, more questions? Tzachi again.
Sure, go ahead. Go ahead.
I need to unmute, I think. Masha,
Okay.
that's how this webinar was organized. Okay.
Yeah, I think, Masha, you may want to let everyone unmute now.
Yes.
It will work smoother. Question, some of the things that you handcrafted now, are you sure that they're not inherently something that needs to be handcrafted, or at least that won't be scalable in the same way that the stuff that you aren't able to scales at the moment?
Right. So what I see is that you can be a lot more intelligent. And we've actually done all those things. So for instance, I can start, let's say I take a system and I have a whole bunch of sensory streams. It's overdimensioned, they've overrepresented and things like that. I look at the results, observe the results that are happening. I can actually then add feedback into my system and actually prune certain channels away or adjust the parameters. So you can start with a massively paralleled, and then you become more and more efficient by basically throwing some material away that's irrelevant. Some channels don't have any information whatsoever. There's no reason to use them. So that's something we actually can think about. And again, we have been playing around with some of that, and it works to a certain extent. So we can actually build the engine a little bit more effective, so that you don't only adjust basically on the data pattern, but you also adjust the computational structure over time and adapt based on the material that I observe.
Okay,
so that's one of the ideas.
So if referring to the diagram you had with the feedbacks, the long-term, short-term,
right,
way back in the talk, do you think all parts of this diagram can be converted efficiently to this kind of computing? Or well, Amdahl come to haunt us?
That's a good question. Actually, I don't think that our brain has an Amdahl problem. So it makes me hoping that indeed we can avoid it. But yes, ultimately, still the engines we're executing are still somewhere have a control engine in there, and then I think that might be the limiting factor for the time being, for sure. But no, I hope ultimately we can get around that. That actually can build you can actually do layers. Actually, Bruno Olshausen, one of my colleagues at Redwood Institute, is playing a lot with this for vision. He's a vision person. And the first step is indeed basically the traditional vision task, finding objects and things like that. But he used this to find relationships between objects and represent a relationship between objects in images and video streams at higher levels of basically representation. So you can imagine that this is a layered type structure, and it doesn't all have to be HD. Maybe, for instance, for the first layer for the image, the object extraction, you could actually use a deep net. Nothing says that you cannot need to have a mesh, as long as you have a way of sending the representation from one layer to the next.
Okay. I think that this is time to say again, thank you, Jan. It was excellent, very interesting. And we hope that next time to see you in Israel after the pandemic.
I hope so too. All right.
Thank you very much.
Thank you.
Okay, thank you. Bye now.
Bye-bye.